PyTorch tips, step-by-step introduction. PyTorch is an open-source deep learning framework used to build, train, and deploy machine learning models. It is commonly used for neural networks, computer vision, natural language processing, recommendation systems, generative AI, research and production ML. A common interview or learning topic is: what are the best PyTorch tips for beginners and real-world projects? This guide explains PyTorch basics, tensors, datasets, data loaders, model creation, training loops, loss functions, optimizers, GPU usage, debugging tips, best practices, common mistakes. Simple definition. PyTorch is a Python library that helps developers build and train deep learning models using tensors and automatic differentiation. Why PyTorch is popular? PyTorch is widely used because: check, easy to learn, Python-friendly, flexible, good for research, supports GPU acceleration, strong deep learning ecosystem. Without PyTorch, building neural networks manually is difficult. Training large models is slower. Gradient calculation is complex. Step 1. Understand tensors. A tensor is the basic data structure in PyTorch. It is similar to kick, number, vector, matrix, multidimensional array. Example: import torch. X equals torch.tensor 1, 2, 3, print x. Tensor examples: scalar means single value, vector means 1D tensor, matrix means 2D tensor, images means 3D tensor, batches means 4D tensor. Step 2. Check tensor shape. Always check tensor shape. X equals torch.rand_n 32, 3, 224, 224. Print x.shape. Meaning, 32 means batch size 3, means color channels, 224 means image height, 224 means image width. Best practice. Most PyTorch errors come from wrong tensor shapes. Step 3. Move tensors to GPU. Use GPU when available. Device equals torch device, CUDA, if torch.cuda is available, else CPU. X equals X, to device. Best practice. Check. Move model to device. Check. Move input tensors to device. Check. Move target labels to device. Step 4. Create a simple model. Example: neural network. Import torch.nn as nn. Class: simple model. nn module. Def init self. Self.network equals nn.sequential, nn.linear 1032, nn.relu, nn.linear 32.1. Def forward self x. Return self.network x. Step 5. Understand forward. The forward method defines how data flows through the model. Def forward self x. Return self network x. You do not usually call forward directly. Instead, output equals model input data. Step 6. Choose the right loss function. Loss function measures model error. Problem type: loss function. Binary classification: BCE loss, BCE with Logit's loss. Multiclass classification: cross entropy loss. Regression: MSE loss, L1 loss. Best practice: use BCE with Logit's loss instead of manually applying sigmoid plus BCE loss. Step 7. Choose an optimizer. Optimizer updates model weights. Common choices: optimizer equals torch.optimatom model.parameters LR equals 0.001. Popular optimizers: AskGD, G, Atom, Atom W. Best practice: start with Atom or Atom W for most projects. Step 8. Basic training loop. Typical PyTorch training flow. Load batch. Forward pass. Calculate loss. Backward pass. Update weights. Example: for inputs, labels in train loader. Inputs equals inputs to device. Labels equals labels to device. Optimizer, 0 grad. Outputs equals model inputs. Loss equals loss fn outputs labels. Loss dot backward. Optimizer dot step. Step 9. Always use optimizer dot zero grad. Gradients accumulate by default. So before each update,
Optimizer dot zero grad.
without this, XX gradients from previous batches are reused. Training becomes incorrect. Step 10. Use model.train and model.eval. Training mode. Model, train. Evaluation mode. Model, eval. Important for layers like dropout, batch norm. Step 11. Disable gradients during evaluation. Use with torch.nograd. Predictions equals model inputs. Benefits. Saves memory, improves speed, avoids unnecessary gradient tracking. Step 12. Build a dataset class. Custom dataset example. From Torch utils data import dataset. Class my dataset dataset. Def init self data labels. Self data equals data. Self labels equals labels. Def underscore len self dot data. Def underscore getting use self index. Return self data index self labels index. Step 13. Use DataLoader. DataLoader handles batching and shuffling. From torch.utils.data import DataLoader. Train loader equals DataLoader dataset. Batch size equals 32. Shuffle equals true. Benefits. Batching, shuffling, parallel loading. Step 14. Save a model. Save model weights. Torch.save model.stateDict model.pth. Best practice. Save stateDict instead of the full model object. Step 15. Load a model. Model equals simple model. Model.load stateDict. Torch.load model.ph. Model.eval. Step 16. Avoid shape mismatch errors. Common issue. Expected input shape does not match model layer shape. Debug using print inputs.shape, print outputs.shape, print labels shape. Step 17. Use .item for scalar loss. Loss value equals loss.item. Use this for logging. Do not use .item before backward. Step 18. Use .detach when needed. Detach tensor from computation graph. Predictions equals outputs detach. Useful for logging, metrics, converting to NumPy. Step 19. Convert tensor to NumPy array equals tensor.detach.cpu.numpy. Important. Detach from graph, move to CPU, convert to NumPy. Step 20. Set random seeds. For reproducibility, import torch, import random, import numpy as np. Torch.manualSeed 42. Random.seed 42. np.random.seed 42. Step 21. Use learning rate scheduler. Schedulers adjust learning rate during training. Example. Scheduler equals torch.optim.lrscheduler.steplr.optimizer. Stack size equals 10. Gamma equals 0.1. After each epoch. Scheduler.step. Step 22. Use early stopping. Early stopping prevents overfitting. Stop training when validation loss stops improving. Benefits. Saves time. Improves generalization. Step 23. Track metrics. Track training loss, validation loss, accuracy, precision, recall, F1 score. Example. Epoch 1. Loss equals 0.85. Accuracy equals 72%. Epoch 2. Loss equals 0.61. Accuracy equals 81%. Step 24. Use mixed precision training. Mixed precision improves speed on GPUs. From torch.cuda.amp, import AutoCast GradScaler. Benefits. Check. Faster training. Check. Lower memory usage. Step 25. Debug gradients. Check if gradients exist. For name, param, in model named parameters, If param.grad is not none, print name param.grad.norm. Useful when C model is not learning, C loss is not changing. Step 26. Start small first. Before training a large model, test with small data. Test with overfit one batch. Test, confirm loss decreases. Best practice. If your model cannot overfit one small batch, something is wrong. Step 27. Use pre-trained models. For image and NLP tasks, pre-trained models save time. Examples: Capital R, ResNet, BERT, EfficientNet, VEET. Best practice. Fine-tune pre-trained models instead of training from scratch when possible. Step 28. Avoid common mistakes. Common mistakes. X forgetting zero grad. X forgetting model eval. X not moving labels to GPU. X wrong loss function. X shape mismatch. X using softmax before cross-entropy loss. X data leakage. X not saving model checkpoints. Real-world example. Image classification flow, images. Dataset, DataLoader. CNN model, training loop, evaluation, saved model. Technologies area tool framework. PyTorch data loading, Dataset, DataLoader. Model CNN, ResNet. Optimization, AtomW. Deployment, Torch script, ONNX. Monitoring MLflow, best practices. Always check tensor shapes. Use GPU when available. Use proper loss functions. Keep training loop clean. Use model.train and model.eval. Disable gradients during evaluation. Save checkpoints. Track experiments. Validate data quality. Common interview questions. 1. What is a tensor in PyTorch? A tensor is a multidimensional array used to store and process data. 2. Why use zero grad? Because gradients accumulate by default in PyTorch. 3. What is the difference between model.train and model.eval? Model.train enables training behavior. Model.eval disables training-specific behavior like dropout. 4. Why use torch.no_grad? It disables gradient tracking during evaluation, saving memory and improving speed. 5. Why use stateDict? It saves model parameters cleanly and is the recommended way to save PyTorch models. Final summary. PyTorch is a powerful framework for building deep learning models. Key tips. Quote, understand tensors. Check shapes often. Check use GPU correctly. Write clean training loops. Choose the right loss function. Use DataLoader. Use train and eval properly. Disable gradients during evaluation. Save model checkpoints. Track metrics. Start small and debug early. Key idea. PyTorch becomes easier when you understand tensors, training loops, gradients, devices, and model lifecycle step by step.